All right, everybody, I think I'm going to go ahead and get started. Hello and welcome. I hope that your day is going okay so far and getting ready for another round of rain, I guess, at the second half of the week here. But hopefully everything's so far so good with everybody. Just want to welcome you back in, and I just have a few announcements to remind you about what's coming up. That we're kind of in a busy period here because we have an exam coming up soon. So I just want to remind you, I'll just put a couple of notes here. There's a homework assignment due tonight, which is homework number 6. So this one is due tonight, and I do have office hours after class as always, and you're also, I'll try to answer a couple of questions during class as well. It's not a very long assignment. There are a couple of true false items. I just want to remind you all, when you're answering those true false items, please try to write down some kind of a reason. I don't need it to be like a long essay or anything too deep or lengthy, but just a one-liner or 1 or 2 lines to just tell me, why was that statement true? Or can you give me an example why it's false? And if you need help with that kind of thing, definitely let me know. On the exams that I'll be giving this semester, I tend not to ask true false on the exam because I don't want people, it kind of creates mind games. You're like questioning, oh, I got 2 in a row that were false, so the next one has to be true or something like that. Instead of doing that, but what I will sometimes do is I will say, here's a statement that is true. Explain it. If here is a statement that is false, give me an example of why it's false. So that kind of thing, I would not hesitate to ask. And so when you see those true false items in the homework, try to treat them in the same manner, that you're going to need to give a little bit of a justification. Anyway, but that's tonight, the homework assignment. There is also one, I know I was doing Tuesdays and Fridays, but this week is a little bit different. The assignments are really pretty short. They should not be taking you very long at all. So the one for number 7 is actually going to be due on Thursday. And it's going to be based on the stuff we're going to cover in literally 15 minutes today. It's a very short assignment. I will take questions on it on Thursday, should there be any, but you shouldn't need more than 20 minutes, maybe 30 if you really want to drag it out. But that's a quick assignment based on the stuff we're going to do today. And then there is a third one this week. Usually I don't like to do 3 in 1 week, but since they're so short, I felt like this might be okay. And the homework number 8 will be based on stuff that I'm hoping to even cover today, but if I have to, I'll spill it into Thursday a little bit. And your midterm is going to cover all the way up through these assignments. So you will want to do them. I'll be very diligent about posting the solutions the day after you turn it in, so that if you do need to review anything on short notice before the exam, you'll certainly be able to do that. On top of this, I am going to be passing out an extra credit quiz at some point, probably on Thursday. I should have that ready. And that'll be something that I would have given in class and given you 20 minutes to do. But since I don't like to use class time for that, you're going to get to do it as a take home, and you'll earn extra credit towards next week's midterm by turning in that quiz. Of course, I'll be grading it for you and giving you feedback on it as well. It should hopefully help you study a little bit for the exam. So there's quite a bit going on, but it's actually, in terms of the bulk of material, it's not so much. It's being split up, chopped up really on a steady basis, because I don't want people procrastinating and doing 3 assignments worth of work on Sunday night when they have a test 36 hours later or something. So that's kind of my reasoning for that. Let me just see. I think that's about it for my announcements. On Thursday last week, I kind of showed you the resources folder for the exam in Canvas, just to remind you that that is up there for your use. Take it or leave it kind of thing. Do as much or as little as you have time for, or that you think you need to do, depending on how you're feeling about stuff. You can certainly target your studying towards what you feel are your weaker points, because it's all in there. There's nothing omitted from that resources folder. So if you're struggling with Bernoulli differential equations, you'll find those in the review packet. If you're struggling with the Gauss-Jordan method, you'll find problems on that in the review packet. It's pretty much very comprehensive. But again, I'm not expecting everybody to do everything from that packet. It kind of is on a case-by-case basis, depending on kind of how you're feeling with the material, okay? So that'll be next Tuesday is our midterm, and you'll have the whole class period to take the test next Tuesday. And there won't be anything else due that day. Just be taking the test pretty much. That'll be it. So are there any questions about kind of where we're headed for the next 7 days or so? Okay, if not, if you think of stuff later, feel free to ask me. If you haven't had a chance to stop by and introduce yourself yet, this is the last week to do that. If you want to be doing these extra credit quizzes and getting credit for them and so on. Almost everybody has made it in now, and I'm getting close to knowing everybody's names, but I'm still working on it a little bit. You can come in Zoom, you can come in person, doesn't make a difference to me. And I will have a lot of office hours, as you know, tonight and also on Thursday and on Friday again. So anyway, there's lots of times that you can catch up with me. Okay, well, it's been 5 days since we've had class. And that means we should probably take a minute and review where we left off. And that was with this very important invertible matrix theorem, right? And this is sort of a long list of statements that if I give you a square matrix, n by n, then all of these statements are either true together or they're all false together about any particular square matrix that you might have, right? So they're all true or they're all false. They are equivalent. They are logically equivalent to each other. And the first thing in the list is that A is invertible, right? So that means everything below in this list, everything below that one is just the same thing as saying that A is invertible. It's just putting it in other terms, right? So AX equals B has a unique solution. We even know what the solution is. You might remember from last week. The solution is unique, one solution, and it is simply A inverse times B. Of course, if you don't have an invertible matrix, then you won't have a unique solution, right? So again, it all goes as a package deal. These statements are all true or they are all false for any matrix that you might have, okay? I skipped some of them. I didn't write down everything from the list. I wanted to focus on really the most important ones. We have the one about the rank of A. This is the number of pivots in the row echelon form of A. Well, for an invertible matrix, it should have full rank. It should be a rank of n, right? So there should be n pivots. In that case, they are going to go straight down the main diagonal of the matrix, right? There's no free variables. There's no columns or rows that are missing pivots, right? There's one in every single row and column. Yeah, so that's for an invertible matrix. And then the Gauss-Jordan method that we learned about last week is just saying that, yeah, if your matrix is invertible, you can do EROs on it and bring it down all the way to the identity matrix. And if you remember the Gauss-Jordan method, doing those EROs will actually give you a procedure for finding A inverse. Right, so that's that Gauss-Jordan method. I won't review that again right now, but you've been working on it on the homework that's due tonight, I think, and certainly we can talk about this some more in office hours if we need to. Anyway, there's nothing here that is particularly user-friendly in terms of like some sort of a go-to test for invertibility of a matrix, but I'm going to add to this list something that will be very helpful for us in just a few minutes, okay? Are there any questions though about what's listed here so far? I just tried to put the highlights right here.
So this is just what we should know for an invertible matrix, right?
Yeah, you want to know all of these things. I think if you really want to feel like you understand the material, you would want to understand all of the statements that go with it. Yeah, this is not just sort of a list that we don't care about. It's actually a pretty useful list. Yeah, good point. Guys, I put a couple of little warm-up problems on my board here that before I go any further, I thought we might practice with these and just see kind of how we're coming along. You might recognize that these are the sorts of things that they would be considered theoretical problems, but they just use the idea of the inverse of a matrix. So let's take a look at these problems right here. The first one just says, suppose we take a square matrix A. And let's just suppose that if we take the fourth power of A, we get all zeros. Okay, then it's asking us to show that the inverse of the identity matrix minus A is the same thing as just the identity matrix plus A squared plus A cubed. Do you guys remember from last week, how do you confirm that two matrices are inverses of each other? What's the go-to procedure for that? Identity. Multiply, I like that. Yeah, exactly. I kind of put that here, right? If you take your matrix and its inverse and you multiply them together, there's no better proof that they're inverses of each other than just getting I, right? So if you multiply the two things together, you should get I. So on a problem like this, which by the way, this is essentially number 35 on this list over here. It's just basically exactly like 35. Essentially what you're going to do is you're going to take the matrix on the left, which is the identity minus A, and you're going to multiply it by what is claimed to be its inverse, identity plus A squared plus A cubed. And what we are hoping is that this equals I. Now, a lot of times I'll see students do this. They'll just write I right there right away. And of course, that's just dreaming of what you're hoping for, right? And we don't want to get too rushed into that conclusion yet. The first thing we really should do is we should try to derive I by working with what's on the board here so far. Okay, so I'm just going to do algebra here, guys. This can be FOILed out. We can like multiply this out, right? We can expand this thing out. So I'm just going to do that. I have identity times identity. That would be identity squared. And then I have plus identity times A, and then plus identity times A squared, and then plus identity times A cubed, right? That's just distributing the identity matrix to all four terms of the second factor. And then I have to take the other term, which is the one that is A, and it has a minus in front of it. So minus A times the identity, minus A times A, which is A squared, minus A times A squared, which is A cubed, and then minus A times A cubed, which is actually A to the fourth. So this is actually what it would be when it's totally FOILed out. Okay, and then the point here is that when you're multiplying by I, right, that's just like multiplying by the number 1. You probably remember it doesn't matter, right? So if I have I times A, well, that's just A, right? And it turns out I also have A times I, which is also just A. So you see, guys, these can just be canceled. Those are both just the same as A. And you can kind of just ignore the I's that you see. So on the next term here, see, I've got identity times A squared. Oh, that's just A squared. And I have a minus A squared right here. So you see, those are also canceled. Those are also canceling. So I'm doing some simplifying with the algebra right here, yeah? I also have identity times A cubed, and then I have a minus A cubed. So most of the terms have canceled out, actually. The only things that we still have here are, I guess I'll go down to the next line here. I still have this identity squared, which I can just reduce to the identity. Remember, I squared is the same as I. And then I have a minus A to the fourth there. And by the way, I didn't really read the question carefully yet. I have to go back to the top. It actually tells us they were giving us a free information that A to the fourth is 0, right? So this is actually just equal to, I guess I'll have to write over here. It's the identity minus 0. Oh, well, that's just the identity. So subtract 0, then you can just drop that off. And guys, that is what we were hoping for. That is what we wanted to see. If we multiply these two things together and prove that it equals I, then that means that the two things we started with are inverses of each other. It's literally this equation right here. Okay? Good enough? Now, by the way, guys, you probably noticed that in the blue writing on the board, if you look everywhere in the blue writing on the board, never did I write anything to a -1 exponent. There is no -1 exponent on anything that I wrote down here. And there's a reason for that. Is that I should not assume that things are invertible before I have shown you that they are invertible. If something is not known to be invertible yet, then we shouldn't be writing a -1 exponent on it yet. And so that's something that is also, I see that a lot, like people will start writing, I'll start seeing like an A inverse on people's paper, and I'll think to myself, did we know that the matrix has an inverse yet? Because remember, only if A is invertible will there even be an A inverse to write down. So be a little careful with that. You try not to put inverses on things unless we know that that matrix has an inverse. And in this problem, we don't know anything about that. They did not tell us that A is invertible. They did not tell us that anything is invertible. We're showing that this thing exists. So we're being asked to prove that there is an inverse for this matrix. But in order to do that, I can't start off by using that inverse. See what I mean? Until I've proven that this matrix is invertible, I shouldn't be writing down an inverse for the matrix. Okay, just a little afterthought there. Questions on that? It's just a slight variation of that to do problem 35 from tonight's homework. So I probably won't do 35, but I'll ask you to kind of mimic what's here. It's almost the same exact problem. Okay, so I'll let you try that one. This second example, this is another thing I might ask you this type of question on a test, which is to give an example of something. But number 2 says, give an example of invertible matrices A and B such that after you add them together, the new matrix is no longer invertible. So this is showing basically that inverses don't play nice with addition, right? If you add 2 things together that are invertible, well, anything could happen, right? But we need to give an example of this. And of course, because you're giving an example, there will be a million right answers, right? There's a ton of right answers, but I want to give you a little hints on how to get to a right answer. First thing is, since you are giving an example, you get to tell me what matrices A and B you want to use. And my question is going to be, what size matrices do you think might be good to work with? I would work with 2 by 2s. You could work with larger matrices, but that's only making it more writing for you. And it's just complicated when it doesn't need to be. I would go with 2 by 2 matrices. And I need 2 of them, A and B, and they have to both be invertible. By the way, the other reason I like working with 2 by 2 matrices is we have a very easy condition. Do you remember for a 2 by 2 matrix, it is invertible if and only if we have this very nice condition. Can somebody remind me what it is?
1 over AD minus CD.
AD minus BC, we don't need the 1 over for the
Oh.
condition, but you're thinking of the formula for the inverse. But yeah, the condition is just that what would be true about AD minus BC? Not equal to 0, exactly. Okay, so what I need is a couple of matrices that are invertible. So A and B are supposed to be invertible to begin with. So let's see, Nathaniel, why don't you tell me your favorite 2 by 2 matrix?
1 0 0 1.
1 0 0 1. Awesome. Let's check that out. Is that invertible? AD minus BC, right? That's 1 times 1 minus 0 times 0. That's not 0. So this is good. This is invertible. And now I need another matrix that's also invertible. But I want to be thinking ahead that after I add them together, that I end up with something that's not invertible. Does anybody have an idea how to do this, Anthony? -1, 0, 0, and -1. I love it. I love it. It's not the only way we could create this outcome for ourselves. But again, AD minus BC right here is not 0. So both of these are invertible. A is invertible. B is invertible, right? Everything's looking good so far here. But look what happens when you add them together. When you add them together, you end up getting all zeros. And now the AD minus BC is 0. which means that this matrix is not invertible. Okay, so that's a great way to do it. If I had used 3x3 matrices instead, I wouldn't have had this nice condition to guide me in constructing the example. So that's why I kind of think it's great to use a 2x2 in this case, since it works out. And this is not the only thing you could have done, but it's a great, very easy example. Notice that these guys were using mostly zeros and ones. There's no need to get big complicated numbers into our examples that just makes the mental math harder, right? So this is very easy to work with, just these nice small numbers here. Any questions on that? Okay, great. So there's a couple warm-up problems for you that I hope kind of helps get us going for today. Well, I want to come back briefly to this invertible matrix theorem. I was mentioning a moment ago that in this list, there's nothing that's very user-friendly here because, you know, to find out if A is invertible, I don't really want to have to do a ton of EROs. To find the rank of a matrix, yeah, you have to do EROs. If I want to reduce it, see if I can reduce it to the identity matrix, I have to do EROs. You guys have done a couple of homework assignments now where you've been doing a lot of EROs and it's kind of a pain, right? After a while, it's like, I don't want to do that anymore. So it would be nice if there was some different kind of test for invertibility that we could add to the list here. And I'm going to do that right now. So I'm going to come back over here. I mentioned this briefly as my sort of soap opera cliffhanger from last Thursday. What I said was that, yeah, we're going to talk about another item in our list. And this list goes on and on and on. We're certainly not done with it at all, but there is something called the determinant of the matrix, determinant of A. And the test is going to be that determinant is not zero. This is simply going to be a number that we are associating with the matrix. So I'm just going to steal a corner of the table here. Yeah, so anyway, I am going to talk about determinants now. And this is actually in chapter 3. And this week's material, guys, it is going to be on this exam that's coming up. So we are going to have to kind of learn this fairly quickly on short turnaround. The good news, though, is that honestly, this is the shortest chapter in the book. And usually for most folks, this isn't too crazy to kind of get the idea behind it. So let's just talk about it now. Determinants. And the idea here is that given a square matrix, an n by n matrix, what we are going to do, so if we assume A is a square matrix, so we're not going to talk about determinants if the matrix is not a square size. It's only for n by n. So the whole class today is only going to be about square matrices, okay? And the idea here is, I'll just briefly mention, is that we are going to associate to the matrix A number, and this number is written DET of A, or there is another notation that mathematicians have adopted, at least as a secondary option, which is to put these sort of absolute value bar things around A. I don't like that notation terribly well. You won't see me using this at all, but I want you to be aware that it does get written that way sometimes. But it should not be interpreted as an absolute value in any way, shape, or form. Okay. So I have to explain how we associate this number to the matrix. And somehow it's going to give us a nice way of testing if A is invertible. That's going to be one of its uses. This actually kind of reminds me of a story when I was in grad school. So I was doing my PhD at UC Berkeley up in the Bay Area. And there was a professor at San Francisco State, which is on the other side of the Bay. And his name was Stephen Axler. He was actually the chair of their department, of the math department at San Francisco State. And he wrote a book whose title was Linear Algebra Done Right. That's what he called it. And I noticed when I looked at the book, there's nothing on determinants in the book. He completely got rid of determinants. And one of the chapters I started flipping through the book, one of the names of one of the chapters was Down with Determinants. And this guy was hell bent on not using determinants. He was going to do linear algebra without ever using a determinant, right? And so his whole book, he doesn't use them. I think he has like in the last chapter of the book, he talks about it like as if it's a footnote or something. He tries to avoid it altogether. Well, turns out my PhD advisor, who's on the other side of the bay, was writing a book also. And I started flipping through my PhD advisor's book, and I noticed he has a chapter called Up with Determinants. And of course, these guys know each other because they're professors, in the same geographic area of the country. And I asked my advisor about that, and he says, "Oh yeah, I love determinants, and I know that Professor Axler over at San Francisco State, he doesn't know what he's talking about." Kind of thing. It's like, and he wrote the book and he called it Linear Algebra Done Right. I don't know, I think it was done wrong. So these two were kind of having a little tit for tat with their books back and forth across the bay. I, of course, had to be completely lined up with my advisor. I was not going to get on his bad side. So I'm going to be in the Up with Determinants camp, and we're going to spend a couple of days learning about these things. But this is kind of a funny how it's a small world out there in the mathematics community. So anyhow, so what is the determinant of A? I'm going to try to explain this now. It's a number. We've already kind of hinted at that. But how do we define this number? Well, I'm going to do this for a 1x1, a 2x2, and a 3x3 to start off with, okay? Which is what most of our matrices will be. So if your matrix A is just a 1x1 matrix with just one number in it, then the determinant of that matrix will just be that number. I'll call it little a. So if we have a matrix with just one number in it, that's the determinant. Not terribly interesting so far. Okay, what if we go up to a 2x2 matrix? So if A is equal to, let's say, A and B on the first row and then C and D on the second row, then I still want to know what is the determinant now. Well, this one is not going to surprise you either because we've seen this expression already. It is going to be AD minus BC, okay? And so sure, we had that little test right here already where we saw that AD minus BC should be not zero in order for the matrix to be invertible. So that's the determinant for a 2x2, okay? So far, so good? Let's do a 3x3 matrix now, okay? I'm gonna write down a 3x3 matrix. So this is a little bit more tedious. Let me go ahead and write out, let's say the first row is ABC, the second row is DEF, and the third row is GHI. So just putting out a bunch of letters to kind of denote the spots of the matrix here. And then I'm going to give you the formula for the determinant again. Oh, by the way, could you do me a favor if you're taking notes on this? Leave just a little bit of room to the right of this matrix here for me, because I'm going to put something in there in a minute that will help us with this formula. But before I do that, let's just write down the formula. The determinant of A in a 3x3 case is the following formula. It will be A times E times I plus B times F times G plus C times D times H, and then minus C times E times G, and then minus A times F times H, and then minus B times D times I. Okay. And we look at that thing and it looks like, oh gosh, and I'm supposed to like memorize this or something. It's a little bit tedious. So it actually, there is an easy way to remember this formula that you won't have to memorize it. And I'm going to show you what that is. The way to get that formula right without having it memorized out in full is to do the following. What you guys are going to want to do is recopy the first two columns. That's why I wanted to have this space here. Just off to the right of the matrix, I just want to recopy the first two columns of the matrix A. Okay, so I recopy those columns. So now I sort of have 5 columns going. And then what I'm going to do, I'm going to use my blue pen here, and maybe I'll use the red one in a minute also. I'm going to make some diagonal lines on this diagram, right? You might notice this AEI is literally just the main diagonal entries multiplied together. So A times E times I right down the main diagonal, that's the first term right here. Okay? And if I then move just one diagonal to the right of that, the very next diagonal is B, F, and a G, which happens to be the next term that I wrote down. And if I move to the right just one more time, I see C, D, and H. And that diagonal is the third term. And all of these, I'm gonna put little plus signs kind of on the bottom of them because those are being added, right? AEI plus BFG plus CDH. And then I'm going to switch colors now, and I'm gonna use a red marker, and I'm gonna draw some more diagonals, but these are gonna go the other direction. So CEG is this diagonal here, and we're subtracting that. So I'll put a little minus next to that arrow. And then again, I'm gonna shift one arrow to the right. And again, I'm gonna have AFH with a minus. And then I'm gonna do it one more time, and I'm gonna get BDI again with a minus. So the red arrows are going with the diagonals where we subtract those products. And the blue ones have the plus signs on them, okay? And so this is how I remember the formula, by the way. I don't have it memorized either. And I like to call this is the so-called arrow method. So this picture here is called the arrow method. And I'm gonna add to that this is 3 by 3. There is no arrow method for a larger matrix. So only for the 3 by 3. I sometimes, every semester, there's usually like one person who tries to use this arrow method on a 4 by 4 matrix, and it will not work. It will not work. So don't let that be you, right? This arrow method is only for a 3 by 3. So for a 3 by 3 matrix, we have that nice formula. Okay. And again, it turns out that as long as that determinant is not 0, after you do all of this crunching of numbers, as long as this is not 0, your matrix is invertible. Okay? Now, for any matrix larger than that, I cannot give you a one-size-fits-all formula for the determinant. So kind of the same thing happened with inverses, and it's happening with this as well. When the matrices are even larger than this, we have to develop sort of more of a procedure for getting the determinant rather than just a straight formula right out of the gate. So let me come back over here so I can talk about that. I'm not going to do any examples on these smaller matrices yet because we're going to see them when we do the bigger ones. I'm still going to be doing, I'll be doing the arrow method and practicing that with you in a moment. Any questions so far though? Yeah, Anthony, go ahead.
On the exam, for us.
Yeah. No, you don't have to use the arrow method. You can use the method I'm about to explain. Yeah, there is another method, and actually later in the semester, we're going to realize that the arrow method is actually not so great, even for a 3 by 3. So it's not wrong to use the arrow method. I encourage it. It's fast. It's nice. But later in the semester, for reasons that you'll see, sometimes our matrices are not going to just have numbers in them. They're actually going to have functions in them and variables. And in those cases, we are actually sometimes going to be better served to not use the arrow method, but rather what I'm about to explain. So that's a very good point. Yeah, you don't certainly have to feel like you have to use it. Okay, so what I want to do here, guys, is I want to talk about what if n is 4 or 5 or 6 or anything larger than that. We've handled the 1 by 1, the 2 by 2, and the 3 by 3 matrices already, but what about larger matrices than that? So it turns out that we need a little bit of a definition here. So I'm going to make a definition for you guys. DEFN, this just stands for definition. I'm gonna make a little definition here, guys. And here is what I'm gonna define. The I comma J minor. Okay, so I'm using an I and a J in these parentheses here, and I'm calling this I comma J, and it's a minor. The I comma J minor, and I will be writing that as M sub ij. So I put a little subscript I and J on it. What is this? This is the determinant. So this minor, Mij, it is the determinant of the n minus 1 by n minus 1 submatrix obtained by deleting. So I'm going to be removing. I'm going to remove or delete row I and column J. All right. So there's some words there that we got to kind of jot down, but this is what the minors are. And I and J is referring to a row and a column. So if your matrix is n by n, then of course you have n different values of I and n different values of J for your matrix. Meaning that you have a whole lot of minors for your matrix. You have M11, you have M12, you have M21, you have M22, right? It goes on and on and on, right? There's a minor for every row column combination, right? So there could be a lot of these, and each one of them is a determinant. This isn't sounding so good. I have all these minors that we can associate with our matrix. So maybe our matrix is 4 by 4. And all of a sudden we have 16 minors. And somehow Dr. Annan is explaining how to find the determinant of A in terms of somehow finding 16 other determinants. That doesn't sound so good. Well, yeah, this is what it is. But what's nice about it is that look at the determinants that we're taking here. It might be 16 determinants, but they would all be 3 by 3 matrices, smaller. You see how the size goes down? You have deleted a row and a column. So somehow you're defining, say, a 4 by 4 determinant in terms of 3 by 3 minors. Now, I haven't explained how that works yet. So far, I've just got the definition up here. In fact, before I actually go any further, I should probably do an example of this. So let's just take an example so we can have a little practice. I'm going to make a matrix A here, and it's going to be 4 by 4. Let's do a 4 by 4. The first row is just 1, 2, 3, and 4. And then in the second row, I have -1, 1, 5, and -2. And then in the third row, I'm going to take 0 and 3 and 0 and -1. And in the fourth row, I'm going to take 2, -2, 1, and -3. Okay. So that's my matrix A. And what I'm going to do, so guys, does everybody understand? There's 16 different minors here for this matrix. I have M11, M12, M13, M14, all the way down to M44, right? All 16 entries. I don't want to do 16 practice sessions right now. So I'm just going to ask you for one of them. Let's just practice on, let's just do M34. Let's just do M34, just for practice. Okay, let's find M34. So for the solution to this, and I don't really need much room for this. For the solution to this, what does it say here? I have to delete row 3 and column 4. So I'm going to cross off row 3 and column 4. And I'm going to take the determinant of the 3 by 3 matrix that's now left, right? So I'm now going to take, so M34 is going to equal the determinant of the 3 by 3 matrix. First row is 1, 2, 3. The second row is -1, 1, 5. And the third row is 2, -2, 1. So this is just the submatrix that I have obtained by deleting row 3 and column 4. Now I got a 3 by 3. We have our arrow method that we introduced a few minutes ago, and I can use that here. I'm going to recopy Guys, I'm gonna recopy the first two columns just off to the right of my matrix, like I explained over there on that diagram. And now I'm gonna do my arrows. I'm gonna do there's 6 arrows here. Let's start with the blue. The blue arrows, those are the ones that are going from the top left to the bottom right. 1 times 1 times 1 is 1. And then plus the next arrow is 2 times 5 times 2, which is 20. And then the next arrow is 3 times -1 times -2, which is actually 6. Okay, so those are the blue arrows. Those all have no sign changes with them. And then I'm going to start subtracting the red arrows, which go the opposite way. 2 times 1 times 3, that would be 6, and I do a -6. Okay, and then the next arrow to the right of that, -2 times 5 times 1, that's -10. I'm subtracting -10. Be careful with these double negatives. This will come up from time to time. And then the last one is 1 times -1 times 2. That's actually -2, and I have to subtract that. So those are the calculations we have. 1 plus 20 plus 6 minus 6 minus -10 minus -2. And let's see, what does that actually equal? 33, doesn't it? 33. The 6's actually cancel. And then you just get 20 plus 10, which is 30. And then you have a 2 and a 1 added together, and you get 33. Okay. So that's the determinant. That's the 3, 4 minor of the matrix. I have not yet explained how that allows you to find the determinant of the original matrix A yet. I still have to do that part. But at least the people understand this idea of a minor so far? Pretty clear? Yeah, Angelica?
So it's I comma J minor,
Uh-huh.
and I'm getting it confused with like,
The I and the J are just telling you which row and which column you are crossing off. So the 3, 4 minor, M3, 4 just means I is 3 and J is 4. So I'm crossing off row 3 and column 4, which is what I did there.
okay, so I comma J is part of the M I J. I mean, it's all the same.
Just focus on this. This is the notation.
Okay,
That's just the notation. Yeah, that's all you really have to think about. Okay, so other questions so far? Well, now there's this related concept. By the way, that's the hardest part of it. Is just understanding how the minors work. There is this related thing now that I'm going to bring up over here, which is the idea of cofactors. So there's one more definition, but this one is pretty easy to kind of figure out what's going on. So I'm going to talk about the I comma J cofactor. So it's going to look very similar to what I wrote down a moment ago. And this is just written Cij. And what is this? This is the following. For this one, I can just give you a formula directly. Cij is equal to, it turns out that it is either equal to Mij as it stands or the negative of Mij. There is a possible sign change, which this -1 is going to facilitate. And I'm going to take -1 and raise it to the I plus j power and multiply that by Mij. So here we go. Cij is equal to -1 to the I plus j power times whatever Mij was. So you can probably figure out that that means, so you guys know, right? If you take -1 to an even power, it's just like 1. But if I take -1 to an odd power, it's like a -1. So what this really means is that you either get Mij or you get negative Mij, depending on the I and the J themselves. So Mij, this would be if I plus j is even, and negative Mij if I plus j is odd. So just depending on which minor you're looking at, that's going to dictate whether you do a sign change or not. So in our example here, in this example from above, can somebody tell me what would be C3, 4? the 3-4 cofactor for the matrix that we've been starting to play with over here? Negative 33, exactly. So the minor was 33, and because 3 plus 4 is odd, there's a sign change. So this just becomes negative 33. Pretty straightforward. So the cofactor sometimes has a minus sign, has a sign change. And it's just in the positions where the I plus J is odd. By the way, there's also kind of a little clever way to remember that as well, which is the following. So this is just a diagram that I like to use, and if you find it helpful, I definitely encourage it, which is you can just draw kind of a little block of a matrix here and just put in kind of where are you going to have to do the sign changes. In the 1, 1 entry, of course, I and J are both equal to 1 and they add up to 2. That's even. And so in that position, there's no sign change. But then if I move over to the 1, 2 position, row 1, column 2, that adds up to 3. That's odd. That means you're going to make a sign change if that's the cofactor you're trying to find. And 2, 1 is the same way, right? But 2, 2, well, that adds up to an even number again, so there's no sign change with that. So this is just helping us remember which positions require sign changes. And the point is it just alternates. As you work your way all the way around whatever the matrix is, this could go on forever. In fact, the way I've got it now, it's not even a square size. This can go on forever. Dot, 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 right? So like 3, 4, the 3, row 3, column 4 would have been right there, and we see that sign change that's required there. Okay. It doesn't mean make it negative, it just means change the sign. See, it's possible that the minor could have been negative, and then the cofactor could have flipped the sign back to positive again. So those kind of things are all going to be possible. Okay. So far, we've only done one example of kind of calculating minors and cofactors, but we're going to do some more. Are there any questions so far, though? If not, we're ready for the big theorem then. We're ready for the big theorem, the one that I've been building to. What if n is 4 or 5 or 6? How are we going to find the determinant of a large matrix? I can now finally explain this, and it is a big result called the cofactor expansion theorem. So this is actually a theorem, and I'm not going to prove this theorem like theoretically. I just want you to know it. And if you really want to see the proof of it, just change your major to math. Next semester, sign up for the Math 307 class. I promise I'll explain everything there. Either that or you can read it in my book too. I do have the details there. But for now, I'm just going to state this theorem. Okay, so here it is. Let A be equal to an n by n matrix. So take your square matrix. Then this is going to give me a formula now for the determinant of A. That's what we're looking for. For any size matrix, this is going to give me a formula. And you can imagine it's going to be a formula that has cofactors appearing in it because it's called the cofactor expansion theorem. It turns out that I'm not just going to give you one formula. I'm going to give you several options to choose from. Actually, I'm going to give you options depending on any row or column that you might like to focus on. Okay, so there's a little notation here, guys, so bear with me. I'll write this down and then we'll make sure everybody follows this. Okay, so the first formula is little ai1 times ci1 plus little ai2 times ci2, and then we go plus dot, 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 little ain cin. And off to the right of that formula, I will recommend that we add a little text to kind of help ourselves remember this. What we're doing in this formula, guys, is we are doing expansion. This is called the expansion theorem. Expansion on row I. Do you guys notice that like all of these A's, I don't know if I ever explained like what does little aij mean? This is just the entry that is in row I and column J of your matrix. It's a specific entry of your matrix. Do you notice that all of the A's that appear in this formula are in the ith row? AI1, AI2, AI3. Those are just, what are the numbers in that row going across from left to right? AI1, AI2, AI3, right? And each of those is being multiplied by the exact corresponding cofactor. So what do I have? CI1, CI2, CIN, and so on. Notice I don't need all of the cofactors of the matrix. Only the cofactors in a particular row, the ith row. So like this is a matrix that has 16 different cofactors. And you're nervous, you're gonna have to calculate 16 cofactors to find the determinant of it. No, no, no. You're going to pick a row, maybe the first row, I don't know. And you're gonna expand on that row. And what that's gonna mean, guys, is that you're gonna multiply these numbers, the 1, the 2, the 3, and the 4, you're gonna multiply them by the cofactors C11, C12, C13, and C14. That's only 4 cofactors that you actually have to calculate, you see. That's pretty nice, not so bad. And you might be wondering, well, which row is it? Is it row 1? It says row I. It's like, which row is it? You get to pick. Turns out that whichever row you pick, you'll get the same answer, or at least you should. And so, by the way, if you were doing one of these 4 rows, do you have a row here in mind that might be a little nicer to work with? Look at row 3. You see, I have A31 is 0, A33 is 0. So out of the 4 terms that you would have had in the expansion formula, 2 of them are 0 before you even take a breath. And so you don't have to do, if you expanded row 3, you would not even have to do 4 cofactors. You would only have to calculate the 2 of them that don't get multiplied by 0, because we all know that if we multiply by 0, we wipe out that expression and just get 0. So it's really nice if you pick your row wisely. Okay. I have even a little bit better news, which is you don't have to be limited to just rows. You can also instead go with a column. I'm going to write down another formula. I promise there's a second formula here, which is going to be a column choice that we would have made. A1J, C1J, plus A2J, C2J, and plus dot, 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 plus ANJ, CNJ. This is another legal formula, and this one would just be referred to as expansion on column J. So you might not like any of the rows to expand on, but maybe there's a column that looks really good to work with. Then you could choose that. Okay? Again, I'm not going to prove this formula right now, but you can prove it. It's in the book. You'll see it in more advanced math classes. But everybody needs to be able to understand this formula, because this is the go-to way of doing determinants for larger matrices. When it's too big for the arrow method, right, you've got this. Okay. Let's just do an example to practice, guys. I think that would be maybe the next thing I would recommend we do. Let's just take a 4x4 matrix again. I'm going to pick a new matrix now. Let's let A be the following matrix: 2, 0, 8, 1 on the first row. I'm going to choose a 4x4 here. And then -1, 1, 3, 5 on the second row. And then the third row is 2, 2, 6, -1. And the fourth row is going to be 3, 0, 1, and -4. Okay, and what I'm hoping we can do together with this is I would like to find the determinant of A. By the way, I forgot to mention, yeah, I keep talking about the homework for Thursday being a pretty short assignment. You know why it's so short? Is because every matrix on Thursday's homework is only up to 3x3 sides. Yes. Which means you don't have to do any of this. This is really for the next stuff. Thursday's homework, you just use the arrow method and do the 2x2 and invertibility tests. Pretty straightforward. And I'll even take questions on Thursday if we need to. But we're really kind of moving into sort of the heavier part of it, which is, yeah, if your matrix is larger like this, it's going to be a little more work to figure it out. Okay, so I think I'm just going to try to do the solution right here so I can keep it all in one place together where we can look at this. Can somebody suggest a row or a column that would be favorable to do the expansion along, right? Look at column 2, everybody. Do you see that there's 2 zeros in that second column? I mean, row 1 would have been okay, but guys, the fewer cofactors you have to do, the better, right? The better. So I'm going to do expanding on column 2. I think it's not a bad idea to kind of write that down for yourself, to just keep clear in your mind what you're doing. And so what is the determinant of A if I use column 2? I'm going to write down the formula explicitly with J equals 2, column 2. So the way this formula would read is A12 C12 plus A22 C22 plus A32 C32 plus A42 C42. That's just writing it all out, kind of in the notation. But as we've noticed, as I think Brighton was noticing when he made his choice, is that A12 is 0. And A42, this is A42, is also 0. So A12 is 0 and A42 is 0. I don't even have to think about those 2 terms. It's only the 2 terms in the middle that I have to think about. Slow me down if I'm going too fast, guys, on this. This is probably the only example I'm going to do in full-blown detail of this. So I don't want to go too fast with it. Now, I can fill in A22 and A32 right away. A22 is a 1 and A32 is a 2. Let's just put those in. So I would have 1 times C22 plus 2 times C32. Now, I'll tell you the other thing I like to do. With these cofactors, you remember that there is sometimes a sign change that we will end up having to incorporate. I have noticed, at least with myself, that I sometimes forget to do that sign change if I wait until the end to do it. So what I'm going to recommend that we do right now, guys, is that we before we actually calculate these things, let's turn them into the minors first, right? C22 is the same as M22 because 2 plus 2, well, you can see from where's my diagram? I erased it. The diagram, right? The plus minus thing. The 2-2 position has no sign change. So the 2-2 minor is the same as the 2-2 cofactor. But C32, 3 plus 2 is odd. So this is going to be a sign change as compared to the minor M32. So I like to just put that sign change in right at the sort of the beginning of this process so I don't forget about it later. And now I've got to do these 2 minors. Okay, let's just figure out what those 2 minors are. Each of them is going to be a determinant. So I'll just go ahead and kind of fill out some space for myself to write this down. Each of these is going to be a 3x3 determinant. So guys, the other thing I wanted to recommend, when you're crossing off, so for the minors, we have to cross off a row and a column. I highly recommend that you do this in pencil or do it very lightly because we're going to end up doing more than one of these and we don't want to get too many lines crossing through our matrix or we won't be able to see what we're doing. The 2-2 minor involves crossing off column 2 and row 2. And if I do that, let's write down the numbers that are left over here. I have a 2, 8, 1 on the top. And then I've crossed off row 2. So I jump down to row 3 where I have a 2, a 6, and a -1. And then row 3 is 3, 1, and -4. Just like that. Okay? And then, so I did that, but now I have to go back and fill in the other matrix. So M32 involves crossing off row 3 and column 2, but now I have to sort of uncross off row 2 here. So do it lightly so you don't get confused with all the lines crossing through your matrix. I'm crossing off column 2, row 3. And let's write down the numbers. On the first row, I have 2, 8, and 1 again. On the second row, I have -1, 3, and 5. And now I go to the third row, I have 3 and 1 and -4. Okay, and so now what I have to do is just do my arrow method if I want. Somebody asked me, do I have to? I think Anthony was asking, do I have to use the arrow method now? It turns out you could choose to use cofactor expansion again, even on a 3x3. Personally, I think the arrow method is easier. So if I have a 3x3, I'm probably going to use the arrow method, but you wouldn't have to. You could choose to cofactor expand this one, and that would be fine. I'm going to try and do these arrows quickly in my head. The first arrow is obviously 2 times 6 times -4. That's -48. And then the next arrow over, I didn't really recopy those 2 columns because they didn't have a lot of room, but it's going to be -24. And then the next arrow over is going to be 1 times 2 times 1. That's +2. And then I'm going to go the opposite direction. 3 times 6 times 1, that's -18. And then 1 times -1 times 2 is that's -2. And then the last arrow, oh boy, -4 times 2 times 8 is 64, and that's a -64. All of whatever that is. Okay, so maybe somebody has a calculator can help me with that in a second. So we have all of that, and then what about this other one? This matrix right here. Maybe I'll just come up here to write this one out. Again, the first diagonal, 2 times 3 times -4, that's -24. So make some room here. -24. 8 times 5 times 3, that's 120. I have to add that. The next diagonal is 1 times -1 times 1, so that's plus -1. And now I go the opposite way again. 3 times 3 times 1 is 9, and I have to subtract that. And then the next diagonal is 1 times 5 times 2, which is 10, and I have to subtract that one. And the third one is -4 times -1 times 8, which is 32, and I have to subtract 32 as well. So that would be the calculation there. So these 6 numbers here. And so let's go back to trying to write down a nice answer. Did anybody figure this out down here yet? I'm serious, I don't have the notes.
-22.
-22, okay, sounds okay to me. And then for the next one, I have -2 times whatever this is. Did anybody work this one out? That's gonna be 100 minus 56, it should be 44.
44. Wow.
44? Yeah,
That
44.
was fast.
I tried. So -22 minus 2 times 44. Now you just work that out. That's 22 and 88 is 110 with a minus. Minus 110? Sound good? I hope so. I have almost all of my lecture notes, but on that one, I didn't quite have that note figured out correctly. So yeah, I think that's probably right. Good enough?
You were fast.
So just in case you're wondering, the matrix that we were working with here, it is invertible because the determinant was not 0. It is invertible. What do you guys think? Does this cofactor expansion method make some sense?
Yeah.
It'll just take a little practice. It's all just crunching numbers, calculating things out. I think, why don't we take a 10-minute break? It's just about 5 o'clock right now. Let's take 10 minutes to stretch our legs, and then we'll practice this on another example. I'm going to talk about some properties of determinants when we come back as well. So go ahead and stretch your legs, get some fresh air. The balcony is probably nice and cool. And we'll start up again in 10 minutes.
My first time.
I think it's just like.
It was, after.
Sorry about that. I've met a lot of people since I've
I
been.
was like, Ronnie's.
Okay, everything good?
I'm going, so. See.
I'm sorry?
It was after we did this.
It's pretty easy.
Fine.
It's pretty bad.
Okay.
There is one, I guess why there is one. That is larger than a three.
No, I know I did.
Oh,
I just said, yeah, yeah, I'm
I'll show
just.
you. You're gonna see this. Yeah.
You
Check it out.
in the phone.
Yeah.
Yeah, you bet.
Yeah.
You can have it done before classes are on. But then you have to take notes too. The samples, yeah. Which ones? Aside from the midterms, I would recommend the review session process. Yeah, and you could watch that with the video. Because then I have a video. That'd be a bad choice, if you wanna focus on something else as well. Yeah, you bet.
Professor.
Hey.
Sorry.
I got your email, by the way, that was not. a
Yeah,
problem.
oh, yeah, I was like.
No worries.
Kind of.
No worries, I hope you weren't bad traffic from.
It's terrible. Yeah, I came from. Lake Forest. Took like an hour.
Yeah, that is not very many miles, but that stretch of road is.
I think there's like 2 more accidents
Than normal.
than.
All it takes is one, and the whole thing gets backed up forever, it's just crazy.
Yeah, just want to confirm that this was arbitrary, right? Because you could just. pick
I just
G.
made it up, I could have done any of them, I just.
You said it'll still all work out.
Yeah, I was just trying to practice with one,
Sure.
one example, so,
Thank you.
yeah, you bet.
So.
Yeah. Well, yeah, because I was like.
I need to say-
I was like, I used to do machine, but it's all the same.
Yeah.
It was just explaining this part.
Yeah.
This is. It's easy. Easiest.
Yeah. Pictures. No, what?
Oh, okay. Okay, she's. Yeah. And I was like, if I get something prepared, but it's fine. I'm just like, oh my God, it's a reminder.
Oh, it's. Yeah.
Take the board.
One
She's
second.
real sweet too. Like, not too fussy, just like a normal little amount.
Yeah. Oh, yeah, that's my house. My house, she was very close.
Yeah.
So,
Just wild. Yeah. How was it?
He just like it.
Yeah.
He's super loud. Even on the bottom of the room, but, yeah, it was quite fast.
You can jump.
I'm already.
I was trying to figure it out. Yeah, you can,
We have
this can get kind of.
I don't want to become
Oh.
that.
But yeah, for turning it out, it's not bad. For bookkeeping, it is.
So you just don't like, okay, I'll play with that. I'm
Yeah.
just sitting there. Sound like something. Which she's already done.
Yeah.
Yeah.
But he makes hard songs with them and
Yeah.
like certain like videos, and she likes them. And so then I was just like, okay, she's hooked. But yeah,
So much. There's like no day where I ever just.
Yeah.
I better not eat right now, I'll get sick.
Just be so.
But yes, I love them.
Trying to keep my life.
Yeah.
I get that like 5 minutes before I go to sleep.
Yeah. And then you fall asleep. You want to do some other stuff. and you fall asleep.
Oh my gosh.
Queen.
That's just what my fingers feel, so how-
Yeah.
And then-
Yeah. I'm still getting used to it. It's just, yeah.
I just
Yeah, you're
accepted
going
it.
through different.
It's a good idea. I stay home and go through this. Yeah, I was,
That's my.
I'm gonna shoot it. But still, it's still like now. So I'm like, there, 'cause I work with the-
Oh my gosh,
Yeah.
way up there.
I live-
Every day.
Every day. Yeah, I have classes
So
every
at
day.
least like 2 hours.
I know it's good.
Yeah.
Yeah, like, maybe they have that. And then just, when you have
Okay. That's it there.
well, it's a corner.
Yeah, I prepared all the chickens out.
Yeah, so I have that. You can get the.
Out now.
Yeah, it's been.
That's the stuff that I learned at the Marco Banks. I got tickets because like, if I have a car sticker and then I can just drive.
Yeah.
Those, I guess, expired like every 2 months or that, something, yeah. And I tried to read my through, they're like, no. It's just-
I said.
And then, so I have it, but then it says like in September, the program within. Yeah.
Did you get a rebate for your car too?
I think.
Yeah.
Yeah.
Nice.
Yeah, I enjoy that.
Yeah.
Yeah, but it's just, it helps, you know, I'm mostly glad that. Because it's like.
Yeah.
Like, it's so.
Yeah. Great. Done this, yeah. Did you start the whole time? or-
Yeah, so.
Or- They started selling that.
Yeah, I bet that, and anything before I was.
It's making sense so far?
But.
Yeah.
I
How the determinants works?
Or
Or are you in the down determinants group?
That, that part.
That's about my favorite.
Okay, it's all right.
Not even now, carbon on the first thing, and then it's off. So it's better to get it out. And then instead of leaving it in the front back.
Yeah, yeah.
I'm not, you know.
Park over by the, like, the engineering building.
Yeah.
Oh, the east side?
East side. Instead of-
Okay, okay. so Yeah. They normally are gonna do it on the for the license and then I charge it and then we'll have to.
It's-
Yeah, they take us with all day.
Yeah. Your whole day. Until.
Oh, and then like right now, because I'm doing all their pockets. It's kind of like your sports. I'm like, guys, I don't have any.
Thanks for letting me steal the corner of your desk here. This is how I do when I go climb my mountains. A lot of times I go by myself because nobody wants to do the crazy mountains with me. So then I take this thing to take my picture on the top. And then I have like 10 seconds to go stand in the right spot. And usually I have to crawl over a bunch of rocks to get there. So it's kind of a little bit dangerous. But it works great for recording this lecture too.
I got the days we left from and these, you know.
What's the last mountain that you climbed? You know, just on Saturday, I climbed a mountain called Pacifico Mountain. It's only an hour from here and it's actually off of the Pacific Crest Trail. You might know there's this trail that goes all the way from Mexico to Canada and it's about 2,600 miles. And I'm not huge into backpacking. So I have not really seriously thought I would do that trail, but I got to walk on 5 miles of it on Saturday and it was so nice because it had rained on Friday. And so there was actually some snow, a little bit of snow. This thing was about 7,000 feet high above sea level. So there was a little bit of snow up there and the trail was so soft and there was no dust. And it's just over, oh, where is that? The western end of the San Gabriel Mountains. Yeah, so that was pretty nice. It took me a while. And then I got to the top and I'm one of these people that they refer to as a peak bagger. It's like I like to climb the mountain and put it in my bag. I did it kind of thing. So, you know, I don't like to just sort of go sort of close to the top because then it doesn't count. Like I didn't really get to the top. So I'm one of these guys, I got to go to the very top. So I get up to this was a nice, just gentle trail all the way to the top. And then there is a 20-foot boulder at the summit. It's like, how am I getting up this boulder? It's definitely like 2 stories of this building almost. And I could have done it, but they didn't tell me in the literature I read, it didn't say that I should bring a helmet or a rope or climbing shoes or anything like that. And I was by myself. I was like, is this a really smart idea? I didn't want to get myself hurt before my big hiking season for the summer. So I crawled up partway up the rock and just said, that's good enough. So, yeah. Oh, well. There's all these debates about what actually counts as being on the summit. Do you have to stand on the summit or is sitting okay? Can you just reach your hand up there? Does that count? Or do you have to get your whole body up there? And you'll start a big argument talking to people about that kind of stuff. Everybody has a different idea. Generally, the people that have already stood on top, they'll tell you you have to stand on top. Everybody else is like, no, you don't. Just have to put your hand up. Yeah. Anyway, at the end of the day, you can just say whatever you want to say, right? It's like it's your own challenge. Just make up your own rules and go with that. All right, I think I got most folks back here again. I think I'm going to go ahead and pick things back up a little bit. Yeah, so guys, just before the break, we took this 4x4 matrix A and we found its determinant. And we did that by using the cofactor expansion method. And in this case, we did column 2, right? So we did column 2 and we chose column 2 because it had quite a few zeros in it, right? Every time there's a 0 in the row or column you're working on, that's one less cofactor that you actually have to think about doing, right? Which makes it nice. So column 2 is very, very favorable here. However, the nice thing about this cofactor expansion is you should get the same answer no matter what row or column you choose. So if anybody wants 7 more practice problems, you could try row 1, row 2, row 3, row 4, or column 1, column 3, or column 4, and you should get negative 110 every single time. You already know what the right answer is, and you can just practice. You would have different intermediate numbers coming into the actual calculations, but by the end of the calculation, the answer should be negative 110. Okay, so just wanted to point that out. And we've got lots of people in here. Maybe everybody would pick a different row or column. But in this case, column 2 is probably the most favorable choice because of all of the zeros. And when you do those cofactors, you have a bunch of 3x3 determinants to do, which of course requires the arrow method. So that's kind of what I've left some of that scribbling on the board there for a moment. But I have another one up here for you to look at with me really quickly. And now look what I've given you. On this example, I have given you a 5x5 matrix. So right away, I'm already thinking about it. The minors of a 5x5 matrix are already still going to be 4x4 because you're going to delete one row and one column. So you're gonna have all of the minors being 4x4s. It's gonna be like 5 4x4 matrices, right? And then for each of those, you have to expand a row or a column, and which brings you into a bunch of 3x3s before you can finally use the arrow method. So you can see how this could get pretty nasty in a hurry. Do you think this one's going to be a hard one to do though? What is nice about this matrix, did you notice? Lots of zeros. Lots of zeros in it. So let's see if we can pick good choices here. If we don't pick good choices, guys, we probably won't get out of here on time tonight. Because it could take a long time if we make the wrong choices. So let's try it. Does somebody wanna be bold and suggest what row or column might be a good one to start with? Row 5. Okay, I like it. Look at all the zeros on row 5, right? So let's expand. I'll just write row 5 here above this equal sign. And the point is with row 5, you're gonna have, 0, 0, 0, 0, and then there's this 2. Is that gonna be with a sign change on it? I guess I have to remember my little diagram here. Plus, minus, plus, minus, plus. They alternate. Minus, plus, minus, plus, right? So it's really, if I really want to think about it, it's plus 0, and then minus 0, and then plus 0, and then minus 0, and then plus 2 times M5, 5. So the 5, 5 minor. I've already incorporated all of the sign changes. I mean, M55 is the same as C55. Right? Because it's a plus right there. Okay, so we're just going across the bottom row like that, and this is all we have to think about. So we have 2 times M55. How do I calculate M55? I cross off row 5 and column 5, and I do the determinant of the submatrix that I'm circling right now, which is a 4x4 submatrix. Anybody have any thoughts about how I might want to actually deal with that 4x4 submatrix for the determinant? I've got to pick a row or a column again, right? Anybody want to propose one? One more time? How about row 4? Row 4 of this 4x4 submatrix looks really good to me, because on row 4, which is this row right here, right, I have 0. So this would technically be, negative 0, right? This is a minus. Negative 0, plus 0, minus 0, and then plus 3 times M44. There we go. Okay, and let me just simplify that. So that's just 2 times 3 times M44. And for M44, I have to cross off row 4 and column 4, and I'm left with this little 3x3 right here. That little 3x3. And I could keep going with the cofactor expansion if I wanted, or I could use the arrow method now. Either way, I'm going to save a little time and just tell you that with this 3x3, if you were to go ahead and expand the third row, you would pick up that factor of 5 right here. And then you would cross that off, and you'd be left with just this 2x2. And for that 2x2, AD minus BC comes into play, and that's just -2 and 3 multiplied together. And that's it. And if we crunch the numbers on that, I think it's -180, just to get a final answer here. And that is the answer. That is the determinant of this original 5x5 matrix. So by the way, this is also invertible. This is also invertible. Now, just looking at that, the -180 isn't maybe so illuminating, but if we just look at what's right before that, we had a 2 and a 3 and a 5 and a -2 and a 3. Does anybody see those numbers anywhere in particular? Yeah. Yeah, cool. They're just right on the main diagonal. I know I've got a lot of scratches through the matrix now, but if you just look at the main diagonal, I have a 3, a -2, a 5, a 3, and a 2. Right? A 3, a -2, a 5, a 3, and a 2. You know what? That's not just a coincidence in this particular matrix. For any triangular matrix. Does everybody remember the triangular idea? This is an upper triangular matrix because there's only zeros below that main diagonal. In this case, guys, the determinant is literally just the product of those main diagonal entries. It's really, really nice, and we should state that for the notes because this is something you're gonna want to use. I'll just call this a theorem. And what it says, guys, is if A, which is n by n, is upper or lower triangular. If the matrix is a triangular matrix, either upper or lower, it works for both kinds, then the determinant of that matrix, we can take advantage of this. It is simply A11 times A22 times A33 and dot, 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 all the way to ANN. Exactly. That's for a triangular matrix. So I think I actually lied to you a few minutes ago. I told you that the homework for Thursday, all of the matrices were 3 by 3 or smaller. I think there actually is maybe one that's 4 by 4 or maybe it's 5 by 5, but it's triangular. It's triangular. So you are going to get the answer in like 2 seconds because you're just going to take the diagonal numbers of the matrix and multiply them together. So that's pretty sweet. Okay. So if a matrix is triangular, the determinant is really easy. If the matrix is 3 by 3 or smaller, it's also really easy. Okay. But I'm wondering, what if this was a 5 by 5 matrix that did not have any zeros in it whatsoever? Plug and chug. Yeah, if there were no zeros whatsoever, then we would be thinking, oh boy, I've got no good choices for a row or a column to do my expansion theorem on. But I don't know what I could do about it. I have to live with it. Or does anybody think they might have an idea what we might, sort of a clever plan that we might use to help ourselves out in that situation? If the matrix has no zeros in it to begin with, have we ever done this so far this semester? We have some matrix and we wanted to get more zeros into it. Because zeros are nice, aren't they? Oh, the EROs. I love it, right? This seems like an idea to me. If my matrix doesn't have zeros in it, no problem. Just do some EROs because we know how to bring zeros into the matrix by doing that, yeah? That's all fine and good, but we do have a little thing we have to worry about, which is if we do EROs to the matrix, are we going to mess up the determinant of the matrix in the process? Right? We do have to worry about that. It turns out we will mess it up. We will mess it up. So if I take a matrix, if I take this matrix right here, which has a determinant of -180, and if I start doing EROs to it, the matrix that I have after that will have a different determinant. It's going to change. But the good news actually is that it will change in ways that we can keep track of. There is going to be some bookkeeping that we can do as we're proceeding through these EROs. And as long as we're careful and we remember, okay, when I do this ERO, this is what's going to happen. And I keep track of all of that stuff, then this actually will work. I can take my matrix that doesn't have any zeros in it. I can hit it with EROs until it is triangular, for example, right? I could make it all the way to triangular, and then, I'll know what the determinant of the triangular matrix is because we've got the theorem for that. The only thing will be, what was the bookkeeping? What were the effects along the way that we need to keep track of? So I would like to have a little conversation with you guys now about how do the EROs affect determinants, right? So let's do that. So this is just a question. At this point, I have not answered this so far, but we're going to look at it now. The question is just, how do EROs affect the determinant of a matrix? How do they affect the determinant of the matrix? So, like I said, I'm gonna answer this in three parts. Like I said, they will affect the determinant, but they will do it in ways that we can keep track of. Okay, so I've got three things here because of course there are three types of EROs. I hope everybody remembers from chapter 2. We can permute two rows. Oh, I'm sorry, I want to write this a little differently. I'm sorry. Let me start over. Let's say I start with A. I start with A, and then let's say that I permute I and J, and that brings me to B. So I'm just gonna write it like that, I think. So if I start with A and then I permute two rows, then here is the effect of that ERO. The determinant of B will be obtained by just putting a minus sign. Okay, really nice. So if I switch two rows, then the price I have to pay on the determinant is just to put a sign change. Easy enough, okay? Let's see, the second ERO was when I start with A and I multiply row I by K. You remember this, right? We take a row of the matrix and we multiply it by K in order to get the matrix B. So let's look at this one. In this case, what will happen is that the determinant of B will actually pick up that factor of K. So you'll just have K times whatever the determinant of A was. Okay, so again, it's not too surprising. So whatever K is, that multiplier just goes through the determinant. Easy enough, okay? And then one more, let's start with the matrix A one more time. Let's do the A operation, Aij of K, and apply that to A, and we get the new matrix B. Okay, so these are the EROs, right? All three kinds of EROs that we learned about. And the question here is, again, what will happen with the determinant? Actually, in this case, I have some very good news for you. With this particular ERO, which we do use a lot, there is actually no effect on the determinant of B. So in other words, in this case, the determinant of B will just be equal to the determinant of A. There will be no change in the value of that determinant, okay? So that's kind of nice. And again, these properties can be proven with some relatively, what I would call cumbersome calculations that are not terribly illuminating. It's not really something I want to spend time with you guys on right now, other than to say, yeah, I want you to know these properties. Okay, so if you do any of these EROs, the determinant might change, but we'll be able to keep track of how it changes. And so if I want to bring zeros into my matrix, well, I will be able to do that using EROs. Alex, yeah. Oh, yeah. So yeah, let's imagine for a second that you see two columns and you would love to like do something with those columns. Technically here, I'm not talking about column operations, but you could achieve that by transposing the matrix and turning those columns into rows and then using these properties and then kind of transposing it back. And it turns out, Alex is bringing up a really good point. In fact, maybe let's make a list of some other properties of determinants here. And then I'll come back to this sort of strategy I'm discussing. When you transpose a matrix, great question. What other properties are there? And it turns out, I'll call this number 4, that if you transpose A, it also has no effect at all on the determinant. So you can transpose a matrix to your heart's content, and there's no problem with that. There's no problem with that at all. Okay. Yes,
So for
exactly.
number 1, when you permute and you add the negative sign, is that for you add a negative every time you permute, or just
Every time you permute,
so if you do it
yes.
twice, then the negative?
If you did 2 permutations, the signs would cancel and you'd be back where you started again. That's a very good point. Yeah, that's a very good point. Actually, that kind of is related to something else. By the way, I love these questions that you guys are asking me. Half the time when you ask me a question, you don't realize it, but you're leading me right into my next thing I want to say. So yeah, I want to make a point here. What would be the determinant of K times A. Let's assume that A is n by n right here. Let's say that I wanted to take the matrix A and I just multiply it by K, the whole matrix getting multiplied by K. I'm wondering if anybody has a proposal for the formula here. Give everybody a minute to think about it. I will tell you the answer is not just K times the determinant of A. Well, we don't know if this thing's invertible. So the A could be any matrix, right? May not be invertible here. Anthony, do you want to try it?
Yeah.
K to the power of n times the determinant of A. That is the correct formula. Now, why is that? Because take a look at this second ERO here, guys. What the second ERO says is if I multiply one row of the matrix by K, then the determinant will factor up by K. But what I'm doing here is I'm not just multiplying one row of A by the scalar K, I'm actually multiplying the entire matrix by K. That means all of the rows. Every row picks up a factor of K, and I've got n rows. So that's why you have to power this K up right here. It's actually K to the n power, right? I see this all the time. I'll give people this example and I'll just say something like, let's just assume that A is 4 by 4 with the determinant of A equal to 5. And then I'll ask them to find the determinant of 2A. Right, I'll just give them something like that. Find the determinant of 2A. And you'd be amazed how many times, I'm just doing the solution right here. You'll be amazed how many times people will say 2 times 5, it's 10. Right, but actually the answer is 2 to the power of 4 times 5. So that's this K to the n, right? The n is the 4 here. So 2 to the 4th is actually 16 times 5, and that comes out to 80. So the answer to that would be 80, right, in this case. Make a little bit of sense? So if I want to multiply an entire matrix by K, the determinant does not just go up by a factor of K, it goes up by K to the n, which is a much larger number in theory. Okay. Great, so that's number 5. I'm going to give you a couple more here while we're still rolling with this list. We could do the determinant of A times B. This would be another one I would like to be able to do. So I'm giving you a little theoretical properties here of determinants. This one turns out that the answer is just determinant of A times determinant of B. So no surprise there at all. No surprise, you just take the individual determinants and multiply them. Again, something like this would be tedious to prove, like in an abstract, rigorous sense, and not terribly illuminating, in my opinion. So I'll leave that for the book in case you want to look into the details of that. But instead, I'm going to go on and I'm going to talk about the determinant of A inverse. Now, of course, not every matrix has an inverse, so don't read too much into this. So if your matrix is invertible, then I might be interested in this formula. But some matrices don't have inverses. Does anybody have a guess as to what that determinant would be? Yeah, it's actually, that's right, Jesus, it's 1 over the determinant of A. It's 1 over the determinant of A. By the way, you could derive that one easily from number 6. Because if you just put A times A inverse, then you would have determinant of A times determinant of A inverse equals 1, right? Because the identity matrix is triangular, right? What is the determinant of the identity matrix? I guess I never mentioned that, but the determinant of I is simply 1 times 1 times 1 times 1 times 1, which is 1. Right. Exactly. Okay, so that's great, but then I have one more item to put here. I'm gonna put it on the bottom of the board, even if those of you in the back don't like it, because this is the warning of the thing you don't wanna do. This is a warning, so I'm not putting this as a property, because this is not a property. But everybody likes to try to do this. I know this because I teach this a fair amount. And the warning is that unfortunately, determinants do not play nice with addition. They do not play nice with addition, and so in fact, there is no formula for this. We really don't have anything we can say. And so we can't try to break this down somehow. So if you see addition of matrices and you want to do a determinant, yeah, there is not a nice shortcut formula to help us with that. We have to kind of just brute force it all the way through. Okay. Yeah, are there any questions about these properties? I know I'm giving you quite a bit to look at here, but this is all heading into this is really 2 homework assignments ahead already. Like I said, the one for Thursday, we've already covered everything you're gonna need for that. This is just getting a little bit further into it. How's my time? Do you have a watch with you? It's about 5:40. I have 10 minutes. 10 minutes. That's amazing. Let me do one last example today where I would like to illustrate this strategy of using EROs to bring some zeros into the matrix. Now, I'm going to do just a 3x3 because I don't want to make this too computationally crazy. But we're not going to just use the arrow method on it, even though it's only a 3x3. I would like to show you this technique a little bit. So I'm going to do one more example and then we'll call it a night. And yeah, so let's do this. Let's let A be equal to this matrix right here. Again, it's a 3x3. First row is 2, 1, 3. Second row is -1, 2, 6. And the third row is 4, 1, and 12. And I want to find the determinant of this matrix. Now again, earlier tonight, I showed you the arrow method. We, of course, could use that. I'm going to not use that. I'm going to imagine that I want to do cofactor expansion. But then I look at it and I say, oh, there is no good row or column here because there's no zeros in this matrix. So here's what I'm going to do. I'm going to use some EROs to bring some zeros into this matrix. So I'm going to just try to do that. And I'm going to do this, guys, fairly quickly just because we don't have a huge amount of time. At least with the EROs, I think we've had some good practice already on this. So I'll just start with A, and I'm going to hit it with some EROs. And I think the first thing I would probably do is permute rows 1 and 2. Okay, yep. So I'm going to take the second row and put it on top. So -1, 2, 6 goes on top. The first row is going to move to the middle, and the third row stays exactly where it is. Okay. Now I'm going to finally start bringing zeros into the matrix by using this -1 and adding multiples of it to the lower rows. So I'm gonna leave the first row alone in this step. And I'm going to do, I want to put a 0 here and here. I'm gonna do them both at the same time, like I always do. And so that's going to be A12 of 2 and A13 of 4. So I'm going to double the first row and add it to the second row, and I'm going to get 0, 5, and 15. So 2 times the first row added to the second row. And then I'm going to take 4 times the first row and add it to the third row, and it's going to give me 0 and 9 and 36. Okay? And by the way, if you decide that you're going to use EROs to simplify your determinant, there's nothing that says you have to go all in on it. You don't have to go all the way to row echelon form or all the way to triangular form in order to declare this a success. You could say, you know what? I've got enough zeros now that I'm just going to stop and do this determinant and then work backwards. do the bookkeeping in reverse. So there's nothing that says you have to go all the way to the end of this process, but I do want to do a little bit more with you here, guys. So what I'm gonna do is I'm now going to multiply row 2 by 1/5. So I'm gonna shrink down the numbers a little bit by multiplying the second row by 1/5, which replaces it with 0, 1, and 3. Third row still stays the same. Okay, and then finally, I'm gonna do A23 of -9. So the first row will stay the same, the second row will stay the same, and then I'm taking -9 times the middle row and adding it to the bottom row to get 0 and 0 and 9. Okay. Is everybody with me on those EROs? Let me know if I'm going too fast. I don't need to rush. I've still got a little bit of time here. 4 minutes?
Yeah.
Okay, I got enough time. This is what kind of matrix? Upper triangular, right? It's upper triangular. And so we have our theorem. The determinant of an upper triangular matrix is just the product of the diagonal values. So this one, so below this calculation, I'm going to start writing out what these determinants are. The determinant here would just be -9, right? So this is -1 times not 1 times 9, -9. Now what we have to do is go backwards through our work and figure out what the determinant of the original A was. So I'm gonna start from -9 and I'm gonna go in reverse here. And there's gonna be a little tricky spot, so don't fall asleep on me because this is a little bit of a tricky issue in a second. So if this determinant is -9, what will this determinant have had to have been?
1.
Now, wait a second. What ERO took place? Well, going from here to here, what ERO is it?
A.
The A operation. What effect does the A operation have? When I do A to B and I do the A operation, how did the two determinants relate to each other? The same, right? So if this one is -9, then what's this one? Also -9, right? Because you just did this A operation, that's all. Okay, everybody with me? Now, what about this one? This is the tricky one. So if this matrix has a determinant of -9, and I'm going backwards through the calculation, so I'm going from right to left when I'm assessing this, what would this determinant have been? Does anybody want to try it?
-45.
Yeah, it's actually -45. So I know that this says M2 of 1/5. And you see the second ERO with the K value here, the K being 1/5. So you look at this, say, well, why didn't you multiply by 1/5? Well, if I was going from left to right, I would have been multiplying by 1/5. But I'm now going in reverse from right back to left. And so I actually have to flip that 1/5 over and realize that going from right to left, I'm multiplying by 5. So I take this -9 and I multiply it by 5. That's how that works. Okay. That's the step that trips people up mostly. The other EROs are usually pretty cool. All right. So then to go from here to here, what is this determinant going to be?
45.
Still -45 because the A operation that goes on in between has no impact. Right. I'm using this stuff here, right? This is the big deal right now. And then finally, what does that tell me for the determinant of A?
It's 45.
45.
I have the P operation, permuting has a sign change, right? So I have to switch this to +45. So that would be the answer. Now, again, at any given point, you could have stopped. There's nothing that says you must go all hog wild, all full in on the ERO process. You could have said, I'm stopping here. And you could have just done this determinant directly right here and gotten an answer, and then you would have had a shorter backtracking to do, right? So you can go from any point and just work back through your steps there. Okay. Guys, on problem 2.6, number 34, if A is a symmetric matrix, it just means that So if you want to prove that A inverse is symmetric, you're just gonna transpose it. And we had a property last week that you can switch these. And if A transpose equals A, you just replace it like that, and that's the whole solution. If you need me to explain that more, I can do it after class, but that's 34 was on the board over there. I thought I'd show it real quick. That's it for tonight, guys. I will see you soon. Have a great rest of your Tuesday evening.
How long